10 seconds later. Good morning, everybody. Welcome back from your spring break. Hopefully you had an enjoyable one. Hopefully yours was a lot cheaper than mine. Seems like everything I have turned around, I have to get something repaired. Once an expensive spring break. All right, couple things. During spring break, did anybody pick up a bottle of vinegar and look at it and say, oh, that has acetic acid in it, carboxylic acid? Or did anybody happen to, I don't know, pick up a bottle of nail polish remover and say it has ethyl acetate and that's an ester? Do any of that? Coming up in a couple of weeks, I'll have to look at the exact schedule, but it's not that far away, is test number 3. And let me remind you, test number 3 will be just like test number 2, except different subject material. It'll cover carboxylic acid, esters, their derivatives, and also amines, amines. Yep, that's all that's on there, and their derivatives. All right. Quick reminder, in case you forgot everything over spring break, there's still 4 bonds to carbon, and we were talking about esters, just in case, a little quick review. An ester carbonyl carbon, double bond to oxygen. That carbonyl carbon has an oxygen with carbons on it. Remember, R and R prime is an organic chemist's way of saying a variable like X and Y in math, something with carbons and hydrogens. And this is an ester. And we talked about how to make esters, and you did this in the lab right before we went on break. By the way, speaking about lab, this week's lab, I just noticed on the syllabus, I think I still have 2A further under, or whatever, part A under the lab 15. If that's the Tollens reagent, don't do that. We dropped that. I came up with a new one because the Tollens reagent on sitting can form explosive intermediates that will make it blow up. So the department, I had no problem with that. You do it right, there's no problem. But the department, about a year ago, got, what should I say, very concerned and said we got to come up with something different. It's too dangerous, even though we've been doing it here for years. And guess what? I did, so I'll hand out. All right. You know, speaking about labs, with the warmer weather coming on, remember, even though I'm not approved, but it's for safety, no shorts, no flip-flops, no open mid-rep, no spaghetti tops in lab. I won't allow it. All right. Quick reminder, how do you make an ester, which you did, and that's Fischer esterification. And I'm going to start you off with your own. Try it, you'll like it, reaction. What would be the organic product or products of the following reaction? By the way, if you haven't figured it out, you're doing very sophisticated organic chemistry, and it doesn't look too painful, and it might even be fun. As you found out in the lab, it's always easier to write a reaction on the board than go in the lab and do it with your hands, natural chemicals. All right, let's take a look at this. question is, what's the organic product or products, and you have to play that favorite game of mine, identify the functional group, look for what's different. Carbonyl hydroxy group carbons, carboxylic acid. Next, what's the hydroxy group on a carbon? Alcohol. Acid catalyst, what do you get? An ester. And question is, what's R? That's simple. What's R prime? What's ever attached to the hydroxyl group? Remember in the esterification, Fischer esterification, the carbon with the hydroxyl group will be the carbon in R prime the oxygen's bonded to. Well, as you know by now, hopefully you figured out Dr. White loves carbonyls, and that's where the action is. I'll write that first. Carbonyl group. Then what's R still attached? The methyl, because you don't break carbon-carbon single bonds. What's R prime? 3 carbons. Which carbon has a hydroxyl? Center one. And that will be the one bonded to the oxygen here. And you make that ester. And as you learned last week, you made 2 esters. Not last week, 2 weeks ago. One that smelled like nail polish remover, and one that smelled like a banana. By the way, does anybody smell a banana or other fruits or vegetables and think about esters? I'm seeing a few converts. My time is running out. I've got to work harder. All right, we've already done this. And once you have an ester, let's do a quick little review. You take an ester, react it with acid and water, you'll break it down. We'll learn later on that this is how your body breaks down all fats and oils. So here's the general reaction: ester, acid, and water. Acid hydrolysis of an ester, ester acid hydrolysis. You get back the carboxylic acid, the alcohol you would use to make that ester. Why don't you try this one out? Boy, I'm being rough on you people. I'm really making you work this morning. I work out. Anybody happen to run into a bottle of bad wine and think, ooh, the alcohol was oxidized to acetic acid? Hope not. Ooh, that would be a good test question. What do you taste when wine goes bad? Chemically. Remember, when you're done, look up and smile. All right, let's take a look at this. The question is, what's the organic product or product? First thing you have to identify is what's different. And if we look, ooh, a benzene ring, but it's on an oxygen with a carbonyl and carbon. This is really an ester, because a benzene ring won't react with acid and water. So this is an ester. What's my R group? These 2 carbons. What's my R prime? A benzene ring. And what are we reacting it with? Water and acid. I can write it either way. And what do you get back? the carboxylic acid and the alcohol you would have used to make that ester. So what's our two carbons? I'm going to start with my carbonyl right here, hydroxyl group, and my two carbons. And next, I'll get my alcohol, and what do I have? A benzene ring. And it doesn't matter which carbon you put the hydroxyl group on. And that's the compounds you get when you react an ester with water and acid. And the nice thing is Mother Nature makes a lot of esters, which allows chemists like me, organic chemists, to react them to make a lot of alcohols and carboxylic acids. We'll learn in a couple of weeks, you'll learn because I already know it, that many of the things you use for your personal care items, skin cream lotion, hand lotion, shampoo, conditioners, and all that, come from esters that have been reacted by acid hydrolysis to make carboxylic acids that have then been made onto other chemicals. I was speaking about this previous reaction, actually not that one, but one of the things I did do, positive thing on over spring break, I came up with an improved method of how to clean a bathtub and all the scum on the walls in the bathtub in actual work time, less than 6 minutes or less. And I'll share that to you when we get into fats and oils. It's an improvement on my other previous method. That worked pretty good too, but this is like, cleans it right off. See all the benefits you have from organic chemistry? And then you could also take an ester, react it with base and water. It's called saponification of an ester. You don't get back the carboxylic acid because in the presence of base, this becomes the carboxylate anion. So you get the carboxylate anion and the carboxylic acid you would use to make that ester, plus the alcohol. And I'll ask you to try this one. What would be the organic product or products for the following? It makes me so happy to see I'm doing organic chemistry. Thank you. All right, looks like the last carbon atoms are just going down. So let's take a look at this. The question is, what's different? Carbonyl, carbon double bond to oxygen, oxygen here, carbons here, carbons here, ester. What am I reacting with? Sodium hydroxide and water. And what do you get? The carboxylate anion of the carboxylic acid you would have used to make that ester, and then the alcohol you would have used to make that ester. And what do we have here? By the way, I've been secretly this whole semester, and I'm still doing it, inoculating you against the chemistry instructor's favorite trick, put a big scary molecule on a test, and students who haven't realized this is this an ester get all confused. Hopefully you're not doing that. You see this is an ester, here's my R group here, here's my R prime. I go with the carbonyl first. And you don't get the carboxylic acid because the carboxylic acid immediately reacts with base to give the carboxylate anion. And my R group are these 4 carbons. And my R prime is methyl. And that's how you do it. And as you'll learn in a couple weeks, seems like I'm saying in a couple weeks, it's going to be exciting once we get into the real world. This is used to make soap. Do you have a bar soap at home? This is one of the ways to make it. And I worked for a company, you'll find out, that we sold, I don't know why they called it that, but the name had been around for eons. We make the carboxylate anion, which is what essentially soap is, then we press them into little pellets and sell them to companies like Neutrogena and all that, and they're called soap noodles. Why they have that name, I wouldn't eat them, but they're called soap noodles. All right, and this is where I finished up last time we met. I hope you enjoyed the little quick review. If you haven't figured out by now, repetition is good for your grade and also helps you learn things. Hi, we're talking about reaction of an ester. And on this slide, I didn't put it there because I'm an organic chemist, we don't balance things. But on my test, I'll make sure I put the 2 there. You take 2 molecules of a Grignard reagent, first step, second step, acid and water. And now you get to do something very special. You get to make not 1, but 2 carbon-carbon single bonds, which is very rare and very special. Keep your eye on the carbonyl carbon. It's never attached to it, it's still attached to it. The Grignard reagents, both of those will bond to that carbonyl carbon, and then from this part, you'll get another alcohol. And generally you keep, when you're doing this in synthesis, R prime very small, so you can distill it out and get your alcohol, the other one you're really trying to make. And since I already went through this, I'll let you try this question.
Yeah, I'm curious why you use R triple prime instead of double prime.
Habit, because sometimes it's a bad habit of mine. I don't know how I started it, but it works. All it means is in math, if you use x, say if you have x plus y equals 50, you could just as easily put z plus y equals 50. And for some reason, years ago, when it comes to this Grignard, this became a triple prime. I guess why do I do it? Habit.
So when I see triple I think to look for a double, and I don't see it.
Yeah. Once in a while, I get sneaky and try and confuse the student. No. One thing I should tell you, on the previous two reactions, I have no problem putting one of those as synthesis. You know, here's the product, what is the starting materials to make this, but on a grid yard, I'll never use that in a synthesis problem. That's cruel, unusual punishment, and as of this week, it's still outlawed by the Supreme Court. I don't know, after this week, if they get a new justice, that might change. But let me keep politics out of my classroom. All right, looks like everybody's done. Let's take a look at this. What do I have here? Ester. How do I know it's an ester? Carbonyl, oxygen, carbons on the carbonyl carbon, carbons on the oxygen, ester. I'll call this R. I'll call this R prime. Now you got me doing it. I put an ester. R prime. And now, what do we have here? Carbon, magnesium halide, a Grignard. And notice there are two of them, which is my way of helping you out. I'll call that R triple prime, acid and water. What am I going to get? Two alcohols. Let's go with the first one. Just keep your eye on the carbonyl carbon, because that's where the fun is. Becomes this carbon. What's attached to it? Methyl. Will still be attached to it, R. What's attached to R triple prime? The carbon with the Grignard will be the carbon bonded to the carbonyl carbon, which is now the alcohol carbon. 3 carbons and carbon. Remember, it's your responsibility that if you see me make a mistake on the board, which I hope I don't, but make sure you tell me so I can correct it. That's the first alcohol. What's the other alcohol? R prime methyl, and you get methanol, which you can distill off. And now I've made this complex alcohol, which I can make into esters, other more complex esters, which I can use for, did anybody happen to smell some very nice flowers or perfume and think of, ooh, that's esters? And that's how you do it. All right. Hopefully you liked a little quick, actually not that quick, but I think it was a good review. And let's move on. All right. Turns out you can have molecules with more than one functional group. In fact, that's quite common in nature, in our everyday life. All you have to do is look at your skin that has more than one functional group, the main one I'll teach you later on. And same thing with many things in our life. They have more than one functional group. And the beauty, and it's a truly beautiful thing and powerful thing, what I've been teaching you, functional group organic chemistry, if you have more than one functional group in a molecule, it reacts like it's alone, unless there are certain exceptions, which at my level I learned in this school, even the 2 semesters, they don't learn the exceptions. But anyways, let's look at something, and I haven't said this in a whole week to you, so I should say it now. One of the things you should always be asking yourself is, why am I learning this stuff? And besides the obvious, somebody said you have to take this class to get in a program or a school, which is quite important to you. Why do they want you to learn this? Because it's in your everyday life. Let's take a look. Turns out you can have a dicarboxylic acid, di means, and you can have a dialcohol, diol, 2 alcohols. And let's look at one dicarboxylic acid. It has the common name of terephthalic acid. How it got that name, I have no idea. Someday when I have nothing better to do, I'll try and search that on the internet. But so far in my life, I have better things to do, and I'll just accept that it's called terephthalic. I'm going to guess, and I might be wrong, but yeah, UPAC would be carboxy benzoic acid. But anyways, and then you have ethylene glycol, which is a diol, 2 alcohols. Well, let's take a look at something. What I'm going to write on the board, do not write down. Trust me, I'm the teacher. All right. Yeah, I'm having a bad ring there. remember earlier today, I went through a review. How do you make an ester? Carboxylic acid, alcohol, you make an ester. Well, what if I take this molecule, terephthalic acid, and on my slide I don't have acid catalyst, but you do have acid catalyst. There are other ways that can make it quick, which I don't go into those functional groups. But anyways, what do I have here? Carboxylic acid. What do I have on this end? An alcohol. And what you get is the following. Again, you don't have to write this down. And you get this molecule. Now, if we look at this new molecule, what has changed? This carboxylic acid reacts with this alcohol to make this ester. Nothing new. There's other stuff in the molecule. Now, if I look at this new molecule, it's got 3 functional groups. Actually, more are considered a benzene ring, but carboxylic acid, ester, alcohol. What if I take this molecule and react it with more terephthalic acid? Well, here I have an alcohol, here I have a carboxylic acid, and what I get is ran out of room at the end there, it's a carboxylic acid. This alcohol reacts with this carboxylic acid to make this ester, nothing new. Now, if we look at this molecule, notice at this end I have a carboxylic acid, and this end I have a carboxylic acid, so I can react it with more ethylene glycol. And also I have acid catalysts here and here. Here I have an alcohol, here I have a carboxylic acid. I get this molecule. Aren't you glad I warned you? Don't write this down. You can thank me later. But anyways, or you don't have to thank me later. And if you look at this new molecule, I have an alcohol at this end. I have a carboxylic acid at this end. And this end I can react with more ethylene glycol. That I can react with more terephthalic acid. And I can keep on building and building. This is called polymerization. We'll talk more about it in depth. For this class, in depth means a whole hour. I could do a whole 2-semester course on polymerization. But anyways, think of a train. How many of you have ever seen a freight train? I think you've all got stuck at an intersection with a long one. By the way, trains is one of my hobbies. Has been since about 5 years old. He's my father. But anyways, what do? They take boxcars and hook them together. And each end of the boxcar has a coupler. They're called knuckle couplers. And you can keep on building longer and longer trains. Well, you can do the same thing with molecules. Now the question is, if you look at this, you'll see a repeating unit. If I were to add more on, this would be a repeating unit, and this is my repeating unit. And if I did this, I don't know, took 500,000 of each together, which you can, and here is the repeating unit, this polyester, poly meaning many, and N can be anywhere in the area of 500,000 to a million. We're talking big trains or molecules. Now the question is, Why is this important? Hold on a second. This has been very tiring work on Thursday. It's good. Really good. Why would this be important? Well, if we take a look at what would be the name of this. Well, poly, because there are many, the ester comes from ethylene glycol, and you know you name the R group, R prime, ethylene, in front of an ester. For the ester, second part, you drop the IC in the word acid and add ATE. So this is called polyethylene terephthalate. Polyethylene terephthalate. Not used to talking after being on break. Polyethylene terephthalate. Plus, I'm thirsty again. Polyethylene terephthalate. That's a lot to say. Actually, organic chemists are lazy. We call it PET, and that's what this bottle is made out of. This bottle is made from the polymerization of terephthalic acid and ethylene glycol. Next time you're in a supermarket or other places that sell anything in a plastic bottle, think about it. These are esters, and it's used, making an ester, to make big macromolecules, which we call polymers, which is this. If you look at the bottom here, it says PET, and that's short for polyethylene terephthalate. And that's why you're learning this stuff, because it's really in your everyday life. Next time you're in the supermarket and you see those 2-liter bottles and you're with a friend, you can tell them, you know that's a polyester? No, you don't have to. All right. Oh no, guess what time it is? It's new chapter time. Now, since you just came back from spring break, I think some of you are still coming back up to speed. Let me do something I rarely do, take a vote. How many would rather wait a week from today to do the problem set for esters and carboxylic acids? Raise your hand. How many would like, well, hold on, raise them high so I can see them. How many would like to do it this Thursday? All right, a week from today, I'll go through the carboxylic acid and esters problem set. Since it's new chapter time, new functional group time, let's go to it. I have time. Oh, I got plenty of time. And this new chapter is called Amines, Amines, and Heterocyclic Compounds. And if it looks like I'm having a good time again, I am. This is one of my other comfort areas. Why is it a comfort functional groups area? Because I made a lot of money working in this area. And it's gotten me around the world. It's paid for my last couple of cars. It paid for my mortgage. A whole lot of nice things in life. So I like amines, amides, and heterocyclic compounds. So far, if you look at the periodic table, I've talked about hydrogen molecules, which everything has hydrogen. Most important element on the periodic table to me, carbon. We've done oxygen, we've done sulfur, thiols, those stinky things, but we haven't talked about nitrogen. So let's talk about nitrogen. Turns out that in Mother Nature's universe, our world, the most common, plentiful organic molecules are those with nitrogen atoms in them. And if we think about nitrogen, the simplest nitrogen compound, one of the rare times I'll put an inorganic molecule on the board, is ammonia. And what is an amine? An amine is a molecule in which you replace the hydrogens on ammonia with carbons. And we call those amines. Now, one thing I should point out, nitrogen, unlike carbon, has a pair of non-bonding electrons. Remember, all elements have an octet, except hydrogen, 8 electrons to be stable, the valence electrons. Well, nitrogen, and it's one of the very rare times, I'll do a little bit of structure. This won't be on the test, but I'll help you. Notice the valence electrons 2, 4, 6, 8 non-bonding electrons. Well, it turns out nitrogen on special occasions can use those non-bonding electrons as to bond with. And therefore, unlike carbon, nitrogen can have 3 bonds to it or 4 bonds to it, 3 or 4. All right, let's take a look at it. If I replace one of the hydrogens with an R group, we have an amine. I can replace 2 of them, still an amine. I can replace 3 of them, and they're amines. Those are amines, nitrogen with carbons on it. And you can have either alkyl group, a ring, or a benzene ring even. I'll teach you some neat stuff this chapter. You'll learn about how do you get your clothes softened. You'll learn about stuff they put in mouthwash to keep your gums healthy. Wow, we get into some neat stuff. All right, and I'll even teach you, I'll tell you a personal story about the snuggle bear. Amazing stuff I'll get into. All right, so nitrogen has 5 valence electrons, 3 more from hydrogen. You have an octet. Well, that means you can replace them with alkyl groups. And form amines. Oops, Steve Ward, had to do something. Now, if you replace one of the hydrogens with an alkyl group, we call this a primary amine. If you replace 2 of them, or put 2 alkyl groups on nitrogen and also has a hydrogen, this is a secondary amine. If you replace all 3 hydrogens with alkyl groups, carbons, we call this a tertiary amine. Now, as I mentioned earlier, you have the non-bonding electrons, which I rarely put, but I'll do today, on the nitrogen, and they can bond on special occasions. Because nitrogen uses both of the electrons to form this last bond, it has a positive charge. All molecules in nature have a net 0 charge. Therefore, I need an anion. There are many anions. I'll use a halogen. Now, convention is you usually write it to the right of the molecule, the anion. But this is actually bonded to the nitrogen, not the R groups. 4 covalent bonds, and this is an ionic bond. This is something I haven't really done much yet this semester. And this has the name quaternary ammonium salt. And I think it's 9 of my 10 patents deal with quaternary ammonium salts. So to say I know something about quaternary ammonium salts is an understatement. I'm a world authority on quaternary ammonium salts. I do consulting in that area still. And I'm going to try to be real good and not drop into shop talk, because in industry, chemical industry, we call them quats. But I'll try not to use slang in this class, just like I've done with ethylene oxide. Just stayed away from calling it EO. And these are the different nitrogen compounds. As of now, you should know. Primary amine, 1 R group. Secondary amine, 2 R groups. Tertiary amine, 3 R groups on nitrogen. And finally, quaternary ammonium salt, 4 R groups. Now, one of the things that confuses students is how many hydrogens should be on a nitrogen when you're writing an amine? Well, it matters which one. For primary, secondary, and tertiary, nitrogen has 3 bonds, and therefore 1 R group, 3 minus 1, 2 hydrogens. Secondary amine, 2 R groups, 3 minus 1, 2, 1 hydrogen. Tertiary amine, 3 minus 3 is 0. And that sometimes confuses students. Well, how do I figure it out? Because quaternary amine has 4 groups, and it also has 0 hydrogens on nitrogen. Since I've worked in this area, and by now you know I teach you what's real world, not just because it's in the book. Nobody uses IUPAC nomenclature for amines unless you're writing a legal document or a patent. Since you're not going to do this in this class, I'm not going to teach you that. What I will teach you is common names, which everybody uses. And for a common name, first of all, let's get an amine up. So primary amine, notice there's 1 R group, so there's 2 hydrogens. How do we do that? You name the alpha groups attached to the nitrogen as the alpha groups they are, and add the word amine. And therefore, this is methyl amine. I'll do this one, then you know I'm going to share. But look at this. What do we have that's different? Now, again, look at what's not carbon, what's not hydrogen. That should get your attention like that. Nitrogen. It's got carbons here, carbons here. It's an amine. What's this R group? Isopropyl. What's this? Methyl. And this is isopropyl. Methyl. I think everybody can see it. You guys see it? Can you see it now? How can you see it? All right. And it'd be isopropyl methylamine, or it could have been methyl isopropylamine. These are common names, so there's no rules which goes first. And that's how you do amines. So let's do some. And the question would be, what would be the common name of this molecule? Remember, those of you who have lab tomorrow and also Thursday, please wear proper clothing, no flip-flops now it's getting warmer, no open midriff, no shorts, things like that. And don't forget to do your to-do list and bring in the lab. And Tuesday's lab, don't hand it in immediately. I think there was one question that I didn't explain properly, and I'll do that at the beginning of lab tomorrow. I corrected that for Thursday. All right, looks like everybody's done. Let's take a look at this. First of all, what's different? Can't look anywhere else. Nitrogen. It's got carbons here, carbons here. This is an amine. What do I have? I have a methyl and propyl. So, again, 3 carbons and carbon and propyl. So this would be methyl N-propylamine or N-propyl-methylamine, either one would work. Now, I think I have on the next slide, this you do not have to learn, but I'm going to show you why everybody uses common instead of IUPAC. The IUPAC rules, which I do know, are similar to alcohols, except the suffix thing at the end is amine instead of OL for longest chain that has the nitrogen attached to it. For secondary and tertiary amines, and this is why Remember a long time ago, I said this is always lowercase? Use uppercase or capital N in front of each other substituent that's not the longest chain. Where additional functional groups are present, the amine group is called an amino group, which we'll get into later on. All right, what would be the IUPAC name? Longest chain is propane. Drop the E, add propanamine, and then this would be 1, because it's on carbon 1 with nitrogen, and we denote that by 1 N-methyl propanamine. Isn't methyl N-propylamine easier to generate? And the answer is yes. So that's why I won't be using it.
Wait, so which one are you using?
Just the common. That's all you have to know for this class.
Okay.
And the ACS doesn't put any back either. Now, there's something I have to talk about, which I haven't done up to this point in the semester. But when it comes to amines, I will be doing that. Is let's look at the following. This is dimethylamine. 2 methyl groups di, we learned that already. I rarely will ever draw it this way. Now I'm going to be using brackets. Notice both methyls are in nitrogen, and therefore that's how I'm going to be drawing it. Another example. I will not draw it this way. Notice on the nitrogen I have an ethyl here. I will draw it, and this is also on my test, and the ACS does the same. These are the same molecules, but organic chemists are lazy, and this is the way I'll draw it. I'll give you 20 seconds. What's the common name for this molecule? Hurry up, time is wasted.
Diethyl.
Oh, we're into bonus time. 5, 4, 3, 2. Time's up. Let's take a look at this way, because this is the way you're going to see it on test. What do I have here? Ethyl group. There are 2 of them. Diethyl. This is N-propyl. And we have diethyl N-propyl, smaller case N, amine. With that, I'm going to let you out a whole 35 seconds early. Remember,